Hey, the Zoom computers. Hey guys, the Zoom computer's working today. Life is good. But hey guys, there we go, we're back online. It's always something. Okay. We have one family of indefinite integrals. We know how to integrate monomials. We understand that the area under the velocity curve gives you the change in position, and you need to add your initial position to it to get your absolute position, not your relative position. And then we looked at the power of the rectangle in calculus. So even though it was very interesting to look at quadratics and trapezoids, and then you could look at cubics, and you can look at other families.
Could you tell me again where the last package was? I checked out his stairwell.
And then the other one is you go past the men's room down that corridor and through the double doors. That's where the receiving station is. Yeah, take a look. Even though other functions where we know the closed form solution could be very interesting for finding numerically an approximate value of an integral, when you're trying to derive formulas, the rectangle is just the easiest thing. And you take it infinitesimally thin, and this application was very easy, but we see that if we think of area as height times width, and the width of the rectangle is delta x being infinitesimally small, the height of the rectangle we're defining to be the difference between f and g, and so we get the total area by summing up the differential areas. So it really almost looks exactly the way we would be doing a Riemann sum. And then one of the things we're going to keep emphasizing is that there's multiple ways to look at an integral. Its fundamental definition comes from area under a curve, and that's really nice because when you've got a curve and you take its area from A to B, and then you go from B to C, that should be the same as A to C. You get the sum from that, okay? The sum of infinitesimal quantities we're going to see today, you're going to derive in class a formula that will almost frighten you, okay? So you may have to take some calming medicine when you get home at the end of lecture, okay? And it also can be viewed as a mapping between functions. So that's what we're seeing here. And you'll be doing in project 1, you have functions, whether they're acceleration or velocity, and you're using the integral to map those functions onto other functions like the position. So there's just different ways to look at an integral. So today we're going to start playing around with how you use calculus to understand properties of robot links. This is a thigh bone of a robot. Does it look like one? Not too bad, huh? So, let's start with our first video. And if you're not hearing anything online, it's okay. There's not much noise being made here with this goat. But if I pause the video, why is the teeter-totter not level? Come on, you guys have a physical idea of how teeter-totters work, right? Then you, yeah. So the thing in the middle is called a fulcrum. And if the fulcrum is under, imagine that goat were really just a point, and that mass were exactly over the fulcrum, and the board lengths were equal and uniform density on both sides, then it should balance, right? But what we would do as kids is we get one kid on one side, one on the other. We wouldn't be the same side, but we would use our feet and just jump up and down. We weren't trying to balance so much, okay? But this goat is balancing. That's interesting. Trying to balance. Okay, now, here's the goat. It's not a point mass. So, roughly, I think you can understand that we need the center of mass, the center of gravity of the goat to be over the fulcrum. How do we calculate the center of mass of a distributed body like that? Okay, so those are the things we're going to do with calculus and a few more. When's the last time you got to have goats in a class, huh? Okay, so let's get started. Come on. Let's get started. Get out of tablet mode so I can get that other window back up. Come on. Thank you, Mr. Surface Pro. Okay, so if I were to put a large mass here, say 3 kilograms, and I put a littler mass here, 1 kilogram, where do I need to put the fulcrum so that it's balanced? You remember some physics about that? Moment arms, Archimedes again, all those things. Should it be in the middle? No, right? It's got to be closer to the heavier mass. How do you determine it's got to be closer to, well, your left, my right, okay? How do you determine where it's supposed to be? Please.
You have to eat with the dogs. The dogs would be the distance.
Let's see if I got that. What you need is this distance, 3 times d1 should equal 1 times d2, okay? Those are called moment arms, okay? So the moment imposed on that. And if you had more masses, the general formula is summation, the sum, I equals 1 to n of xi minus xc times m equals 0. And I'll define all these terms. Sum of the moments equals 0. Okay, so this is mi. Position of mi. And this thing here is called the x component of the center of mass. And if you're used to the term center of gravity from physics, that's fine. They're exactly the same thing. So center of mass. And we'll write center of mass in shorthand, something like this. And then this is our unknown. Whoops. We assume the positions of the masses are known, and so we can just solve this equation very quickly, and you would obtain sum I equals 1 to n of xi times mi over the sum I equals 1 to n of mi. And so this is, and this is the total mass. And I could be so kind as to draw a picture and label a few things if you wanted. X1, Xi, whoops. Who knows, maybe this is X7. And you would add up all those terms, and then XC is where you need to place the fulcrum. So XC is the balance point. Okay, so that's the notion of center of mass and equilibrium and balance when you have just discrete masses. Okay. Now, suppose we had a more complicated situation. You know, I'm not going to draw a goat. But I could attempt to draw something like, let's go. Like this robot thigh I had here. And I won't put any holes in it, so that's my poor, grizzlified drawing of this robot thigh bone, okay? And we'll label this top function f of x and the bottom function g of x, and my point B is out here. So we know how to calculate the area of that. How would we calculate its total mass? So to do that, we need some assumptions about the robot link. Okay, so density is normally defined as mass divided by volume. Now, if you just look at this, all you see is area, there is no volume. But if you turn it sideways, it's a thin plate, right? Small thickness. And even though it's not uniform, I'm going to pretend this is a uniform thick plate. Okay, so this is X, Y, and Z. And so the assumptions about the link is that it's constant thickness in the Z direction. And the density and one often uses the symbol, Greek symbol rho. is constant throughout the link. Okay, so on this little toy, it's not exactly constant, okay? And so you should do a more complicated model of how the density is varying in X and Y. Because this is not a course in mechanics, we're going to keep the simplified assumptions, but when you take a more advanced course, you can learn how to do that. Have you had to calculate masses of more complicated things? All kinds in ME, right? If you can't do that, you can't call yourself a mechanical engineer. Okay, so, well, how would you get then the total mass of this object? Well, from calculus, we got total area by adding up differential area. We should get total mass by adding up differential mass, okay? So M total is the integral from A to B of dm of x. Well, what would that be? Let's take a point x. It's just like our area calculation. Put an infinitesimally thin rectangle here. So that's the width. Okay. What is the height of my rectangle? F minus g. It's just like the area. So I'm going to take the area times the density, and that'll give me my differential mass. So dm of x is rho times dA. Excuse me, should be d volume. And the volume I get by taking area times the thickness. Okay, so equals rho times h times differential area. Once again, constant thickness in the z direction here. And so we're not doing the integral yet, Grizzle. So it's rho times h, f of x minus g of x, that's the height of the rectangle, times its width. Okay, so that's a differential mass, dm. At the point x, differential mass. Infinitesimally thin, so we want the total mass, we just add them all up. So then the total mass equals the integral from A to B, differential mass of x, and that's the integral from A to B. Density times the thickness in the z direction, f of x minus g of x times dx. So it's nearly identical to the formula for area. And the reason for that is that the thickness is constant and the density is constant. If the density varied along in the x direction, then we would have something slightly different than the formula for area. Okay, so does that make sense? Makes too much sense? Okay. So how do we find the center of mass? Okay. Where's it at? Is it here? I mean, it's going to be closer to this end than this end because it's thicker here. Let's pretend the hole's not even there, okay? Just to keep it simple and more or less matching the drumstick that I've drawn up here, okay? It looks like a turkey drumstick, okay? Hey, Grizzle does what he can, okay? And at my age, you're not going to change me, right? So that's it. So where is it? Can you tell? Can you just by looking at it? Is it here? No. More this way? Here? Getting close, right? Now, the center of mass, should it just be in this direction or should it be up and down as well? Now this, because it's symmetric, it's going to be right down the line, but my drumstick is not so symmetric, so there's going to be some offset, okay? Now, the way I have my drumstick, this is X, right? So when I balance it, this thing is trying to, here it's not balanced. About what axis is it trying to rotate? If this is X, and Z is the thickness, so that's that, what is this axis? Thank you. X, Z, we got it, we got Y, okay. So what we need to do then is look at the distance of masses from the Y-axis when we're doing the balance here. And then if we were doing here, so this part is Y, and then we're trying to balance that. So this is Y now, this is Y. This axis is then the other one, X, okay? So Z is, because we're doing math 116 right now, okay, we're not doing math 215, we don't have Z. Okay, so we've got the total mass. Let's start working on center of mass. For our distributed I should say our link with distributed mass would be better English. You can make your notes better than mine. Okay, so let's look at the center of mass there. So physics, just like for the point mass, it's going to say that the integral from A to B of x minus xc times dm of x equals 0. Okay? xc equals center of mass in the x direction. That's unknown. And that's what we're trying to solve for. X is a variable. X is right here. It's the position that we are in this object. So we know that. We've already calculated the differential density, the differential mass. So that was rho h times f of x minus g of x quantity times the differential width, dx, okay? So an integral of a sum is the sum of integrals. We can break this thing up just using basic calculus that we've looked at. So we get the integral of x dm of x equals, And I'm going to take the constant xc out of the other integral. Okay? And then just like we did with the discrete masses, I had a sum I equals 1 to little n on both sides. And I recognize this is mt, our total mass. And this thing has a name. It's my, the moment about the y-axis. And once again, we're moving here in x, and the axis about which this thing is rotating is the y-axis, so it's called my. In the current version of your textbook, I have those flipped, okay? Go figure, okay? I don't know how that happened, okay? But I wrote it, so I know who did it. I don't know how it happened, but I know who did it. Okay, so in your next edition, it'll be all fixed up. But this is rotating about the y-axis, so it's called the moment about the y-axis, my. Okay, and so we just solve for xc. We take what's on the right, multiplying xc, and divide it by what's on the left. And all we got to do is fill in integral from a to b, x. And this was rho times h, density times thickness, times height, times width. Okay, there's my. And then this is the total mass. And this is rho times h. The moment about the y-axis divided by the total mass. So that's the x position of the center of mass. Okay, so it's still not much more complicated than when we got area, but it's the same general idea. We started with one simple principle from physics that the moments need to balance. And if you understand that for a discrete mass, all we did was replace the sum with an integral, because that's what an integral is. Okay, replace the point mass with an infinitesimal mass, and then that sigma becomes a lazy s, and from the 1 to n becomes from A to B, where the mass is distributed. So this is how calculus allows you to take simple things that you would have learned in like probably physics 140, okay, and turn it into something that works for a real live physical object where the mass is not concentrated at distinct points, but is distributed. Okay? Excited? A little bit? A little bit? Okay, so this is once again the second way of looking at integrals. An integral is a fancy way to do sums of infinitesimal quantities. And once you understand that, you get these beautiful formulas popping out that then you will do these calculations using quad GK or your own implementation of Simpson's rule or trapezoidal rule, et cetera. Okay, so unless these functions, and you know, this one looks fairly complex, unless these functions are really simple, you're not going to find closed form solutions. So this is why you need numerical methods. Okay, so that's the moment about, because we defined this to be the x-axis, okay? Now we got the moment that's when we're dealing with this. That's more interesting. Okay, so let's try to figure out, so finding YC, the y position of the center of mass, Whoops. Why did you come disconnected? Come on. Y position of the center of mass. Whoops, you should just write COM here. And this is interesting in the sense of the famous Chinese proverb, may you lead an interesting life, okay? Which is a curse, meaning interesting, like lots of trouble, okay? So that's what this means. Okay, I need to draw my drumstick again. Sorry about that. Whoops. I have axis tool. 1, 2. Okay, so Z, Y, X. I might make my figure just a little bit simpler this time. Not a whole lot, but just a little bit. And it can be below the axis. They just need to be functions. Okay, so let's take, once again, dx. Let me try to make these things straighter so it really looks like a rectangle. And it doesn't have to be so differential because you guys are using your imagination anyway. Okay? Now, what we need to compute now is how the mass in the y direction is, how is it distance from the x-axis, because that's how it rotates in this direction. Okay, we just did this direction. Now we want to rotate it there. So if this is actually a rectangle, because when you take it super small, it is. And remember, this is f of x, and this is g of x. You should be blue. Okay. Where is the center of mass of that rectangle? Remember, the thickness is constant and the density is constant. So where is the center of mass of that rectangle?
The center
This,
of that rectangle.
yeah, so we don't need to worry about the, where did it go? Whoops, it's up here. This is infinitesimally thin, so everything here is the center in that direction. But in the y direction, where is the center of that rectangle? It's in the middle. And what is the formula for the middle, given the top is f and the bottom is g?
So it's f minus g divided by g.
Okay. How about f plus g over 2? Yeah, because if this were -1 and that were 5, then you would add that and then it would be at 2 in the middle, okay? So it's the a plus b over 2 is the middle. So the middle is right here. Whoops. The middle is right here. I'm going to call that, this is x. I'm going to call this y of x. And y of x is equal to f of x plus g of x over 2. That's how you calculate midpoints between two numbers. So f of x plus g of x over 2. Okay, so now we need to integrate to get mx. We already know the total mass is going to be the integral from A to B of the distance of the center of mass from the y-axis times the differential mass dm of x. So that's for rotation now with respect to the x-axis. If that red dot were exactly on the x-axis, then it would balance and it wouldn't want to rotate at all. If the red dot is above the x-axis, it wants to fall in that direction, and if it's below the x-axis, it wants to fall in the other direction. Please.
When you're doing like dm of x, what is like the x in the parentheses represent? Like 2, is that like, are you like multiplying?
Oh, when I'm doing this,
Yeah.
it's that my differential mass varies. You know, the question is, why am I calling differential mass as a function of x? Because I have different mass over here because the object is thicker in the y direction, even though it's the same thickness, the height is different. Then I have here, which is, I chose there the absolute lowest point. So the amount of mass I have, these are the same widths. And because they're differential, they're truly rectangles. I have more mass in that infinitesimal left one, so it varies with where I am in the object. So here's x. Here I have a small amount of mass, and because here it's thicker, I have more mass. And so I'm just saying it varies with where I am in the object. No, it's a great question, okay? And most books, you won't see it written down, the explicit dependence. They'll just say, yeah, they'll just say dm, and then you have to realize that it's, oh, the differential mass here for the same tiny thickness, width, excuse me, thickness is this, the width, for the same width, it's more mass here than here because the object is less high. The height is shorter. That's what that means. And then now it's algebra. And that differential mass is still rho times height. And then the height of the rectangle, which was the difference, times dx. Okay, so call this alpha, beta in your mind, and this is alpha and beta. So you have alpha plus beta times alpha minus beta. What does that equal to? X plus y times x minus y, if you prefer, is x squared minus y squared. Okay, so you get a, okay. So we get the integral from a to b, and I'll put 1/2 density, thickness, f squared of x minus g squared of x dx. And then yc is mx over the total mass. And so doing these calculations by hand is a real nightmare for most realistic robot links. Fortunately, when we do things in CAD, they compute all this stuff for us, okay? But if you were doing the design and you wanted to just, get your favorite coding scheme out, whether it's Python or Julia or like I learned Fortran, C++, et cetera, then you just code up a numerical scheme to evaluate these integrals, and you get center of mass and moments of inertia. And so, yeah. This is quad GK to the rescue, okay? Or for the win if you want. And all I mean by that is it's very rare that we can find nice closed form solutions unless it's a sphere or something else really simple, and that's why in a standard calculus class they never work any nice examples, because they only want ones where you can get simple closed form solutions. Okay, so once again, the key point here is that everything is possible because we view what we're trying to compute as first understanding it for an infinitesimally wide portion of the object, and then we add up the contribution across the object. Is that cool? It is very cool. Sorry, that's a superpower of calculus. That's really what calculus is for. Calculus is not designed to drive undergraduates crazy. It's not designed to drive faculty crazy for correcting exams where undergraduates make sign errors and all this kind of stuff, okay? Calculus is designed to take physical principles, understand them on small portions of an object, and then extend that knowledge to the whole thing. And if I had just written down for you that this is the moment about the x-axis, you would have just stared at me like I was from Mars, okay? Now you'll go back and you'll say, okay, I can do it. And then for the x-axis, it was much simpler. Notice that there's no squares or anything. And the reason the y was more interesting is that because we have a uniform body, we could calculate the distance of the y contribution from the x-axis as y of x being the mean of f and g, and then add up all of those contributions. We're happy? Okay, we come back, we're going to do moment of inertia. We'll break early here.
A long pull! Well, you fall when your center of mass, basically your body's balance point, goes outside the base of support, or your feet. At that point, there's nothing to support you against the pull of gravity, and you topple over. But if you add a pull with weights on each end, look what happens. Adding the weights pulls your cumulative center of mass below your support base. So toppling over now requires it to move up. Gravity is now your friend. It constantly pulls the center of mass back down to stabilize things out. It's the same thing with these balancing bird toys. The wings are weighted so the center of mass is actually below its balancing point at the beak. Although holding the pull low does lower their center of mass.
Okay, first of all, we saw the symbol for center of mass here that I didn't have written down. Usually it's black and white. So where it's yellow here in the video, it's white. For the circle, divide it into 4 quarters and you color it black. That's the symbol for center of mass. If you see an object and you see that on there, that's how they label it. Okay? But here, what this is showing, the importance, we were looking at center of mass as this thing that is basically important for static balance, okay? Here it's showing it also contributes to understanding whether something can be dynamically balanced as well. And this object, okay, when the center of mass is low, it's trying to right itself. So this is important for boats, for example. That's why they have a keel and weight in the keel so that the center of mass is below the center of pressure. Here the pressure is being defined by the weight of the object on this rope that this fake rope is on, okay? And the center of mass being below that allows one to balance. Where is it? Okay, here. Now here, where is the center of mass? Is it above the rope or below the rope? It's above. Okay? He's walking up the table. So what's the purpose of the long bar? It's not really changing his center of mass much, okay? A little bit.
Increase the moment of inertia, so it's not going to like turn at all.
Yeah, it's the same thing that we do, okay? Yeah, so what we're going to look at next is moment of inertia, which is another important thing. And if you are building a robot and you want it to run, should you put all of the mass in the feet, which is very far from the hip, distal, far away, or should you try, you can't make the mass zero or the robot's going to collapse, okay? So how should you try to distribute the mass in order to make it easy to swing the legs? And you guys know this, if you've ever put on heavy boots for snow or something, it's much harder to walk and you run much slower. And track people try to wear shoes that weigh a gram or 10 grams or something, okay? And there's a reason for that, because it affects the moment of inertia. So what is moment of inertia? You understand that mass is resistance to acceleration. Okay, so if I apply the same force to a bus that I apply to a ping pong ball, which one is going to be accelerating more quickly? The ping pong ball, right? Because it has lower mass, lower resistance. Now, for rotational things, it's not force, it's torque. And is it easier to go like this or to go like this? You guys tell me. Look at ladies first. For once, it pays. It's Zoe, so. Is that easy? No, try the other. Yeah.
Oh, this one's harder.
Much harder. The object weighs the same, but the mass distribution is different depending upon where the pivot point is. Okay, so what are you playing around with there? You guys come on over if you want to play with it. You
They don't use huge weights, and that's because the biggest benefit of the pole comes from the length. These two rods weigh the same, but when I spin them with the same force, the shorter one rotates way faster than the longer one. That's because the longer one has more rotational inertia, meaning it's harder to rotate. So if you hold a long pole, that actually makes you harder to rotate as well. And you actually know this, which is why when you're trying to balance,
Having
you
fun?
automatically put your arms out. But there's another trick to stay on a tightrope that doesn't require a pull at all. And it's actually one of the real.
Now this is different. This is balance using feedback control, and that's what your project 3 is about with the Rob 311 ball bot. Okay, that's a different kind of balance. Have you guys seen videos from this guy before?
I love Mark Rook.
Yeah. So he's done the Glitter Bomb series. You guys have watched that with Glee, with the Porch Pirates, okay? And he runs Crash Lab, what's it called? Something. Crunch Labs, yeah. So he's got lots of good content that is mathematically and physically interesting and yet explained in a clean and simple way. Okay, so we're done with the goats, but so let's look at moment of inertia, and what we're going to do is once again, come on, open. We're going to understand moment of inertia for a point mass. And then we're going to write down what is the infinitesimal moment of inertia when we have distributed masses and teeny tiny masses. Then we're going to add them all up. That's calculus, that's integration, okay? So Calculus is a machine for deriving important formulas from really simple concepts. Okay. So you'll have to catch that later. Okay, so and ours will be about the z-axis. Oh, and again? Oh, come on, just the connector. It's not my laptop. I'll start bringing my own. But thank you. About the z-axis. So, x, y, and then here's z. So we're going to be doing rotation. Well, it's easier for me to do this, okay? It's going to be doing rotation about the z-axis. Okay, that's physically what's going on. So, okay. R is the distance of our mass from the origin. Okay, so for a point mass, the moment of inertia about the z-axis is by definition equal to r squared times m. That's not calculus, that's physics. Okay, so it's the distance to the origin, and so r is equal to square root of x squared plus y squared. This thing has an x coordinate and a y coordinate, and so r squared is simply x squared plus y squared. So that's how you do moment of inertia for a point mass. We want to do it for a distributed mass. So let me set up another set of axes. Okay. What about a body with distributed mass? So it's spread out. It's not clustered in a point. A to B. Same game as before. We have functions. Oops, that's a G. Looks like a Q to me. So we have a body that's upper bounded by f of x in the y direction and lower bounded by g of x. Okay? And its extent in x is from A to B. So guess what the width of that is? dx, right? Okay, now we're going to do a little tiny bit of two-dimensional calculus. Okay, and this point is x. And this point, that's the y coordinate. So our body lies in the xy plane. Its extent in the z-axis is a constant thickness h, and we're assuming uniform density, no holes, okay? So differential mass is still density times volume, and the volume is going to be the thickness, h, and then times dx and dy. So dm of x and y this time, so it depends not just on x, it depends on where I've drawn this little tiny rectangle that is dy high, dx wide. So this is my density times the thickness in z times dx times dy. I've already written down what r squared is, but let's show it. So that's r, the distance of this infinitesimal piece of mass from the origin. So that infinitesimal piece of mass acts like a point mass. The moment of inertia of that is r squared times dm. That's okay, so here r squared, is equal to x squared plus y squared. Okay, so the little bit of inertia to that tiny piece of mass, which is dx wide and dy high, is going to be r squared times dm of x. What I want us to do now is to compute the moment of inertia of this entire strip. Okay, I want us to take this entire strip and compute its moment of inertia about the z-axis. And then once we know how to handle that strip, we will integrate from A to B, because we will add up the contribution of the mass clear across the body. Okay, so what we're going to do is first calculate the moment of inertia of this little strip rotating about the z-axis, and then we'll integrate here. We've got two integrals to do. We need to add up in y, and then add up the whole thing in x. Ooh. Whoa, that sounds hard, okay? That's math 215. Don't say the dirty word, okay? So I'm going to get you going, but you're going to have to do. Okay, so this is for the rectangle. This is going to be the integral, and we're integrating in y. And so in y, it starts at g of x and goes all the way up to f of x. And so I'm going to write that in a way that makes it easier for us to keep track that we're integrating in the y direction. But we're just adding things up. That's all integrals are. R squared of xy, and I don't know why, but I'm putting my differential mass. Okay, so that's really the definition. And so we're integrating along y. With x being constant. And why is x constant? Because x says the position of this rectangle, and we're just adding up the masses in that rectangle, and that's in the vertical direction, the way I've drawn the picture. Okay, so let's fill this in a little bit. Y equals g of x to what equals f of x. R squared is just x squared plus y squared. And the differential mass is rho times h times dx times dy. I'm going to put, whoops. I'm going to put everything that doesn't depend upon y in a different color, okay? So we are integrating, so people online, I'll try to do it here. X is constant. X squared is a number, pi, okay? It's just a number. Y is the variable. Rho, that's constant density, h is a constant thickness, and dx, that's constant too, okay? So what I want you guys to do, because you know, I want you to now evaluate this integral. Okay, well, write down what you need to do. And you guys know that if I was doing the integral from, say, c to d of a constant dy, that's y evaluated from c to d, which is d minus c. And you know, integral from c to d of y dy, that would be y squared over 2 evaluated from c to d. And then let me squeeze in another one. C to d, y squared dy. That's just using what we know about monomials. Okay? So you guys know those integrals. They're definite integrals. So do it. Okay? So these are constants. Whoops. Come on. These are constants. You can just take them out. So you need to integrate this constant with respect to y and this variable with respect to y and evaluate them from g of x to f of x. Do it. And tell me what you get. And if it's not the most awesome integral you've ever derived, I'll be disappointed. X is a constant, rho is a constant, H is a constant, and dx, we're not changing the width. We're integrating vertically. Too easy for you, Max?
I gotta start and see.
You got to start and see. Okay, you've got the integrals written down, so that's what you've got to integrate. It's got two pieces, the constant piece with x squared and the varying piece with y squared. How are we doing online? James, making good progress? If you get a formula, feel free to put it in chat. Or turn on your camera and hold it up to the camera. That might be easier for you. I'd be happy with that, and so would Max. I guess your snacks made James hungry. Life is hard. Can you find something snarky to send back to James? He doesn't deserve snarky, but yeah, he does. He's having dinner while we're working. So in this, your C is g of x, and your D is f of x, right? That's what you're plugging in. I see dancing fingers, I see dancing hands, I see. Okay, I'm going to finish it up, but I think when I do it, it's going to make a whole lot more sense because you've struggled with it or maybe you actually have it, okay? So we're going to take the constants outside. Integral from g of x, the bottom of the length, to y of x, the top of the link. And I'll keep my x squared black because it's not changing. Okay, and then the integral of a constant, so we end up with rho times h times dx. So this is x squared times y plus, whoops, come on, I had blue, plus y cubed over 3, evaluated from g of x to f of x. And now I'm just going to plug everything in. Rho times h times dx. This is x squared, and the y evaluates to f of x minus g of x. And then plus, can I squeeze that in? I think so. This is f cubed of x minus g cubed of x all over 3. How many of you got that or something really close? Wow! Is that the most awesome formula you've ever derived in your entire undergraduate career? Close, isn't it? If not, it's very close. So now, how do we get the total contribution? We know the moment of inertia of this rectangle. How do we get the total moment of inertia of this body about the z-axis? We just add up the contribution of each of the rectangles, and that's it. And we get a doubly awesome formula, okay? So now Iz equals the integral from a to b of diz. And that's the integral from a to b and, I don't know, rho h. Those are constants, but now the x is varying, so I don't have to put everything. So this is x squared. And I want you to go home and find a case where you can do this by hand. And I'm just kidding, because unless you take a rectangle or something super symmetric, you're not going to do it, okay? And then note that the dx, it's traditional, right? It's traditional that we put it at the end of the integral. There's no rule that says you have to put dx there. I mean, if you left your dx here, it'll probably be marked wrong in 85% of your engineering courses, okay? And you'll be slapped on the hand for it. But there's no law that says the dx can't go someplace in the middle. It just has to be in the integral. But we always write it at the end. And if you do something that someone's not expecting, they're going to mark it wrong, okay? That's all it is too. So isn't that cool? And once again, you you need numerical methods to compute this. Was that almost fun too? At least it was interesting. Okay, fun. Okay. Let's watch the last of my videos, and then we'll go on to something that by comparison will be less fun. So when I come back and ask this question, was that fun? You'll go, oh yeah, that was really great. So at the end of video 2, it was essentially this. Is it easier to rotate like this, where the mass is near the axis of rotation, or where the bigger part of the mass is far from the axis of rotation, and you all experience that this is much harder to rotate? Okay, so you have physical intuition now and mathematical know-how to go with it. Do we agree? We'll see. Okay.
Which discs will reach the bottom of the ramp first? They weigh the same, they're the same diameter, the only difference is one is solid and one is hollow. 3, 2, 1. But wait, before we can see which wheel will win the race, we first need to understand the physics at play here. All right, so I've got 2 sticks here, each one with 2 apples on them. So when I move them,
remember apples. if you just put apples in your brain, you're always going to remember this story about moment of inertia, okay? This is why this guy's brilliant. He gives little simple metaphors that most organic brains can absorb, okay? So remember, he started out with a ring and a solid disk. They both have the same mass. Do they both have the same moment of inertia? Well, you guys were saying, well, if it was, it would be kind of a dorky video, right? So the answer has to be no. But do you know why? You gotta speak louder because you got a deaf professor up here.
For one, the mass is evenly distributed, and for the other, most of the mass is around the edge.
Okay, so I think the answer I just got is that one of them has, there's no mass here, and all of it is out here, so all of it's far away. And the other one is, imagine that this is sort of like in the middle, okay? But watch his apple analogy, and then you won't forget this, okay? Come on.
But now let me try and rotate them. Hold up, this is rotating way slower than I can rotate
Same
this
thing
one.
as this.
Actually, that does make sense. The further away your mass is from the center of rotation, the harder it's going to
R
be to
squared.
move it.
R
because you
squared
just have to move
matters.
that mass a greater distance. This one has its apples evenly distributed
Its
from
apples
the center
evenly
to the edge,
distributed.
whereas
Okay.
this one has all of its apples around the edge. Now, which one is going to be easier to rotate and therefore get to the bottom first? Think of your answer in 3, 2, 1.
Go!
Boom! Which disc will reach the bottom of the ramp first?
Okay, so we figured out. And it's because inertia is resistance to rotation, just like mass is resistance to acceleration. Okay, so that's what's going on here, okay, to displacement. Okay, so that's the end of chapter 3. And we've done, a few applications of integration. First one, area between two functions, boring. Getting the total mass of an object, slightly more interesting looking, but it was really the same thing because we had constant thickness and constant density. And then when we started going to center of mass, it became a little bit more interesting. And then moment of inertia, we got this formula that we can go home and show our friends, and they'll say, wow, you're a genius, okay? I derived that in class in 5 minutes, okay? So, now that we've had all this fun, we get to do more limits. Excited? Excited now? Were you relatively more excited watching Crunch Lab, okay? And doing moment of inertia. So yeah. So that was our table. Okay, so this is chapter 4. And I'll just give the short title, Properties of Functions. So what we're covering here in chapter 4 is usually what's done in the first 3 weeks of Math 115, when you start with differential calculus instead of integral calculus. So the beauty, in my humble opinion, of doing integration first is that most everybody understands sums. And the only limits we need are limits at infinity, and that's somehow more intuitive because it's the steady state behavior of a function or something depending upon n. And yes, we gave an epsilon n characterization where epsilon was the precision of getting around the steady state value of the function. And n, for you guys, would go this way for x positive. N was how far you had to go out to stay within that level of precision. And you get smaller and smaller, so more precise, tighter bounds. You have to go farther and farther out unless the function's constant, in which case it doesn't matter where you are. Okay, so those limits are just fundamentally easier to understand. So this is the toughest chapter in the book, though I think for you guys it's not a big deal because you are calculus pros. There are no Crunch Lab videos. The fun factor is low. But the payoff is high. And of course, it's the latter part why we're going through all this grungy stuff, okay? Because we need it to really understand differentiation correctly. And then we're going to need it to, when we do some really cool applications of the derivative. So this first part is going to be, I think, fairly intuitive. Make it a little bit smaller. Okay, so we're going to talk about left and right limits at a point. Okay, so let's focus on the point 0. This is the function, and I'm going to approach it from the left. That means from smaller values than 0. What is the limit of the function as I let x get closer and closer to 0 equal to 0? Nobody wanted to say it because it's too obvious, okay? It's 0. Similarly, if I approach it from the right side, here my function is constant, so yeah, the limit is easy to evaluate. It's 1. Okay? So the way we write that is the limit as x approaches 0 from the left of f of x was 0. So the minus means approach through smaller values, which we'll just say is from the left. And the limit as x approaches 0 from the right of f of x was equal to 1. And the plus means approach from the right of 0. Now, do we only able to do that when the function is piecewise constant, etc.? I don't know. Let's pick a different point. 2. If I approach from the left at 2, what do I get? 1! We're so excited. And if I approach from the right, what do I get? 1 again! Now, notice on these things, when we're approaching, we never evaluated the function at 0. We approach, but we never equal that point. So the function can have some strange behavior at that, and that's why limits from the left and right allow you to focus on its asymptotic behavior as you approach from the two sides. And the same thing here. Now, you don't have to just do that. Let's take the point 3. If I approach from the left, I get 0. And if I approach from the right, I get 0. And it's the same as the value of the function. Now, would you say this function is continuous at this point? Yes, I'm not tricking you, okay? So what happened there? Limit from the left equals limit from the right equals value of the function. That's continuity. That's the big message of this chapter. And then we'll see consequences of understanding continuity as something more in a deeper way than just, can I draw the graph without lifting my pencil from the paper? Now this point, 0, is the function continuous at 0? And you would go, no, okay. We learned that in 3rd grade or something, okay, because I had to lift my pencil from the paper to draw it, so it's not continuous. Now, what about this point? 2. The limit from the left and the limit from the right, they're the same. They're both 1. Is the function continuous there? No, there's still a jump. So the limit from the left, limit from the right is not equal to the function. So have that in your brain when you think about continuity or discontinuity. That's what's going on. Okay. Now let me ask you this. When we're doing limits at infinity, so for you guys, infinity is this direction, positive infinity, okay? When you're going there, did you think about it as being a limit from the left? Wait a minute. Yeah, left. Okay, I had to turn around. Okay? But it is a one-sided limit because you're going to plus infinity or to minus infinity. You're going to one side or the other. Now, when you did the limit, did you ever reach infinity? That's not part of the definition. You can't reach it because infinity is a concept. It's not a real number, so you never evaluated the function at infinity. You just looked at its characteristics as you got closer and closer to infinity. So all of those things are going to apply when we do limits from the left and right carefully. And once we do that, the rest of the chapter opens up for us. But if we're struggling with that, okay, so observation. I'm using a Greek letter, eta. When eta is positive, 1 over eta is also positive. And if I take the limit as eta goes to infinity of 1 over eta, I get 0. Because 1 over eta is positive, we are approaching 0 from the right. We're approaching 0 from the right. The right side of 0 is denoted 0 plus, because we've approached it through positive values. Okay, we didn't go through negative values. Similarly, if I take my little Greek letter eta and I make it negative, then 1 over eta is negative. And it's still true. If If I take eta now goes to minus infinity, and I look at the simple function 1 over eta, I get 0. But this time we are approaching 0 from the left. Go away. The left side of 0 is denoted, 0 minus. We're good with these concepts? We know how to do limits at infinity. What I'm showing you is that with limits at infinity, we know how to do limits from the left and right at the origin, okay? Let eta go very big, 1 over eta is small. If eta is positive, we're approaching from the right, and if eta is negative, we're approaching the origin from the left. So we know how to do limits at a point, one side and the other, through our understanding of limits at infinity. So we're just going to make a preliminary definition. The limit as x approaches a point x0 from the right of f of x is by definition equal to limit as eta goes to infinity f x0 plus 1 over eta. Okay, we're adding a positive number to x0, and we're letting that positive number become smaller and smaller. So we're approaching it from the right, okay? And then you guys see my devious pattern here. X approaches x0 from the left at x0 is by definition equal to limit eta goes to infinity. Eta goes to minus infinity. Minus infinity. F of x0 plus 1 over eta. Limit from the right. Oh, turn your brain back on, Grizzle. We're not done yet. We're almost done, though. Okay, eta is negative. 1 over eta is negative, but it's getting smaller and smaller. We're approaching from the left. So I want us to do 2 limits, and then we can go home. Grizzle, turn your brain back on. F of y equals y squared. I wrote the y squared as the argument of the function. I mean, you can do that, but it's not what I wanted to do, okay? F of y is y squared. Okay, so I want you to tell me the limit as y goes to 0 plus of f of y and limit y goes to 0 minus f of y. Quicker you do it, quicker we're out of here. Start on my right side, the left side of the room. So what's the limit as y decreases to 0 from the right of y squared? Okay, I see somebody making the hand sign for 0. I'll accept that. Now, if you put 2 of them, that's infinity, right? Or is that love? Okay. What's the other limit? The same. Yeah. Cool. B. F of theta equals undefined when theta equals pi over 2 plus or minus k times pi, k equals 0, 1, 2, blah, blah, blah. And it's tangent of theta otherwise. Ooh, that looks more challenging. But if you get it, we get to go home. So what's the limit as theta approaches pi over 2 from the right of f of theta equals, and what's the limit as theta approaches pi over 2 from the left? Feel free to draw a graph, okay? Help yourself out. It's tangent theta, and you know tangent theta is periodic, period pi, okay? Draw the graph, and at pi over 2, you're dividing by 0, so it's not defined there. And the same thing for 3 pi over 2 and minus pi over 2, etc. So I'm approaching pi over 2 from the right. What is tangent of theta doing? Much easier with the graph, isn't it? Okay? So when you get these tricky problems, just make a sketch. So we're almost done. If we approach from the left, where is tangent headed to? Plus infinity. And if we approach it from the right, it's headed to minus infinity. Okay, so we do this kind of a little bit on steroids, but that's pretty much it. So at 6:17, we're done. I don't feel too terrible ending this way because we had so much fun with moments of inertia and center of mass and deriving the most awesome formula that you've ever done in your undergraduate career. And this is the end of the week. So we've completed 3 weeks, 4 weeks? Oh, wait a minute. It's 4, yeah. 3? Yeah, something like that. Yeah, so anyway, we're 3, 4, yeah. Yeah, because we had all those half weeks to start, and then the third one was a half week. Yeah, so it's really, we've completed the 4th week of class. We're started chapter 4. You'll get through that, and then you're going to really love chapter 6. 5 will be for you guys review, but I think you're starting to see that you're understanding calculus in a little bit more fundamental way than maybe you got in your math courses, which is weird. I'm an engineer. Well, why is that possible, okay? Shouldn't be possible. And then I don't know if you saw the announcement, we have an official number now for Rob 298. It's now Rob 201. It's no longer a special topics course. On your transcript, it'll still be a special topics course. That sucks. But it becomes official for the class in fall of 25. There was a lot of resistance to the course becoming official. That's what I heard. I wasn't at the meeting. And it seems much too daring to do what we're trying to do here, okay? So it'll be up to you guys to set the record straight. They don't believe me because I'm too biased, okay? So anyway, it's been fun. I'm getting to know you guys. I enjoy your personalities. Thank you for showing up. It's really fun to have you in the classroom. So thank you. Bye. Good night.